Hey guys, the purpose of this video is to review what we discussed before we left for Thanksgiving break. So the idea behind chapter 5 is all about angles. So we discussed that an angle always starts in standard position, which is at the 3 o'clock position here. At this point it is considered 0 degrees. Which we know a full rotation beyond that takes it to the 360 degree mark, which ends up in the same place as well. Remember, counterclockwise is considered the positive direction, and clockwise is considered the negative. So if I take this ray in standard form and I rotate it some amount of degrees counterclockwise, remember that's positive, I'm going to end up in the third quadrant, and we call this the terminal side, just because it's where the angle rotation ends. Then we took those angles and we got them rounded to degrees, and then we could say, okay, well, let's further convert that rounded degree into minutes and seconds as well. So this is where the latitude and the longitudinal measurements of our globe come into play. Degrees, minutes, and seconds give them much more precise location, whereas just degrees rounded to the nearest thousandth per se gives only an approximation of where that should be. So we're going to do an example of each. We're first going to take the degree. Let's do 194.828 degrees. And if I ask you for that in degrees, minutes, and seconds, remember, I want you to be comfortable with using a calculator as well as doing this by hand. And hopefully in the next couple videos, I'll let you know for sure what you'll be able to use for your test. But for now, let's review both. If you go ahead and type in 100 and whatever number I just said, 94.828 in your calculator, if you then hit second angle, it opens up this list here, and number 4 says DMS. So then it will take your angle, DMS, convert it to the minutes and seconds as well. So as a final answer, this one would actually be 194 degrees, which is obvious. And then it's going to be 49 minutes and 40.8 seconds. So that's super quick. By hand, it's really not that bad either. Essentially, you know it's going to be 194 degrees already. Let's do a different color. So if it's already 194 degrees, that's one part. Then you need to just take the decimal and convert that to the minutes and seconds. So we'll take 0.828 and multiply that by 60 to get our degrees. So if we do that, then we end up with 49.68. So that implies that we're going to have 49 minutes, and then you're going to take the 0.68 there, multiply it by another 60. So that's going to be 40.8, and that's where the seconds comes into play. And again, that's the same answer we should have gotten there. 149 degrees, 49 minutes, 40.8 seconds. And it's okay if that seconds is in a decimal as well. You're going to see that occur sometimes. We also can go from degrees, minutes, and seconds just into degrees. So if I take, let's do 37 degrees, 29 minutes, and 44 seconds. And if I want to convert that just to degrees, we're going to use the second angle in the alpha plus key to actually enter that in the calculator exactly as we see it. So if we do 37 and then do second angle, and then number 1 is a degree. I don't even know if you can see this calculator right now. So 37 degrees, 29 minutes is number 2, and then 44 to do seconds. Again, we're going to do alpha plus, and then just hit enter, and that's going to go ahead and give us our degrees as a decimal. We're going to round that to the nearest thousandth is generally what we'll do. So it's going to be approximately 37.496 degrees. By hand, it's also not very complicated, and kind of one fell swoop you can type this in the calculator. Essentially what we're going to do is we know it's going to be a full 37 degrees. 29 minutes can be written as 29 over 60, and then 44 seconds can be written as 44 over 3600. Remember, that is considered 60 squared because we have to do the conversion from minutes to seconds. And then if you add all of that up in the calculator, make sure to use parentheses around these fractions. You should also get that same decimal there. So this reviews the conversions between degrees rounded and then degrees, minutes, and seconds, which is a little bit more precise. So the next few things that we did were we took those specific angles and we talked about different aspects of them. One of the things we discussed was how we can take a number of rotations and figure out, okay, exactly where on that 360-degree circle would this terminal side land. So if I take an array starting off in standard form and I wanted to know how many degrees a 6.4 clockwise rotation would take it, what we need to do is we simply just are going to multiply 6.4, but instead of multiplying it by 360, remember the keyword here is clockwise, which is considered a negative direction. So we're going to take 6.4, multiply it by negative 360 degrees, and you should end up with a negative 2,304 degrees. So that's where that would end up landing after that many rotations. So then we talked about examples where I asked you for all of the angles coterminal with a given angle, and then just one angle that's positive and one that's negative coterminal with that as well. So let's first recall what the word coterminal means. Co meaning both, terminal means where they terminate. So I mean angles that will both start off in standard position and will end up landing in the same spot. Well, remember we discussed that coterminal. To find that, all you have to do is add 360 over and over and over again, or subtract it over and over and over again. So remember, there are an infinite amount of coterminal angles, so you can't list them all. So if I ask you to describe all of the angles coterminal, here I'm just using 192 degrees as an example. To list all of them would be impossible because they're an infinite amount. So simply what we need to do is take that 192 and describe in such a way all of the other angles simply by adding 360 degrees k. Now, remember k is an integer which could be positive or negative, so that takes care of adding 360 degrees however many times, as well as subtracting 360 degrees as many times. If I ask you specifically for one positive and one negative, well then you can go ahead and say, well, okay, 192 plus 360 degrees, I know that's going to give me another positive, which is 552. And then if I ask for one negative, then we could do 192 minus 360, which will give us negative 168. And again, sometimes if this number is too big or too little, you might have to add a few times or subtract 360 off a few times. It's not always as simple as just adding 361 or 360 once and then subtracting 360 another time. To take coterminal angles another step further, instead of just asking you for any coterminal angle or a positive or a negative, sometimes you're going to be asked for a coterminal angle specifically that lies between 0 and 360 degrees. So if that happens, like it does here, I'm asking you for the coterminal angle between 0 and 360 of 1,507, and I want you to name the quadrant in which that's going to land. This is going to take a little bit more work. So I'm going to take 1507, but if I just subtract 360, that's not going to be off far enough for me to get down between 0 and 360. So there are lots of different ways you can do this. Sometimes if the numbers are small enough, you can just keep taking 360 away as many times as necessary, which I believe is 4, in order for this to occur. So if you subtract that off 4 times, or do just 1507 minus 360 times 4, and you could just alter that number in your calculator however you want to do it, you're going to end up with 67 degrees, and then the 67 degree angle is going to be in quadrant 1. So sometimes this is going to require you adding 360 a bunch of times or subtracting off a bunch of times, and so your final number gets down to between 0 and 360 degrees. Something that's going to be extremely helpful for us as the chapter moves on is how to find a reference angle of something. So remember, there are basically these types of, I'm going to say, formulas, depending on which quadrant the angle lies. Now, quadrant 1 is our friend. If the angle lies in quadrant 1, I'm going to call that alpha, then the reference angle is itself. If the angle lies in quadrant 2, then we have a little bit of work to do. We're going to take 180 degrees minus alpha to find whatever the reference angle should be. And if it's in the third quadrant, it's similar, except it's going to be alpha minus 180 degrees. And then lastly, in quadrant 4, we're going to have 360 degrees minus alpha. Now, these only apply to if the angle itself is between 0 and 360. So sometimes what you're going to have to do first is find the actual reference angle. For instance, if I give you 500 degrees, that's going to be in 300, the third quadrant, hopefully. Let me check that before you try to go ahead and start correcting me while I'm not there. Yeah, 140 degrees. So that's going to be in the second quadrant. And if you do 180 minus 500, then you're getting a much large negative number that doesn't really make sense for a reference angle. So typically it's a good idea to find your coterminal angle between 0 and 360 first, and then go ahead and do whatever expression is necessary to find the reference angle. So if I give you something like, if I ask you to find the reference angle of 271 degrees. First, determine where that angle lies. Now, it's already between 0 and 360, so you're good on that front. Remember, this is 270 degrees, so 271 is going to push it to quadrant 4. So to find that reference angle, I'm going to take 360 degrees minus 271 degrees, and that reference angle is going to end up being 89 degrees. So that one's pretty plain Jane straightforward. If I ask you to find the reference angle for negative 113 degrees. So remember that what I said, this one's going to be a little bit of a challenge. Starting at standard position, negative 113, this will be negative 90, so it's going to be somewhere in the third quadrant. But then when you take negative 113 and subtract 180, I'm getting a really big negative number, which means my reference angle is not going to make much sense. So the first thing I want to do is find the coterminal angle between 0 and 360. So find 0 to 360 coterminal angle first. So if I do that and I take negative 113 and I add 360 degrees to it, then I end up with, I did these calculations earlier, 247. So then that 247 degrees, again, still in the third quadrant, we didn't change where it went, we just changed the coterminal angle of it. Then if I take alpha minus 180, so 247 minus 180, I end up with 67 degrees. So that angle of reference will be 67. Now remember, reference angle should always be between 0 and 90 degrees. So no matter where it starts off in the other quadrants, the idea is that your final answer is going to end up between 0 and 90. So all of what we reviewed so far has been from section 5.1 of your textbook. In 5.2, we started talking about trig ratios. The big mnemonic device here that you need to remember, and that you're all pretty familiar with at this point, is SOHCAHTOA. Now, remember, all a ratio is a comparison between two numbers. 2 to 5, wins to losses, boys to girls, typically given in fractions. So if I ask you for ratios of this triangle here, now granted I'm missing a side right now, eventually you could give me 6 total. So it's really important that we understand that the ratios came from a need to have a name for the particular ratio. Like 12 to 13 has a different meaning than 13 to 12. So we have to discuss which ratio stands for which numbers, okay? So I'm going to go ahead and put some angles in here. We'll call that theta. We'll call this alpha. And I want you to give me the 6 trig ratios, both for theta and for alpha. Now, first thing we need to do is go ahead and solve for this third side here. So if we go ahead and say, okay, well, 12 squared plus, we don't know what that is. You can call it b squared or x squared equals 13 squared. So it's going to be 144 and 169. So 169 minus 144 is going to be 25, which is great because then when we take the square root of both sides, remember, typically you're going to have a positive and a negative answer. But since we're dealing with distance, we're going to completely disregard the negative answer and just go ahead with the positive 5. So if I ask you for the sine, cosine, and tangent, and cosecant, secant, and cotangent of both of these, we should notice some patterns. So let's just do theta first. So if I do the sine of theta, that's going to be opposite over hypotenuse. So from theta, I've got 5 over 13. The cosine of theta is adjacent over hypotenuse, so that's going to be 12 over 13. And then the tangent is going to be opposite over adjacent, so it's going to be 5 over 12. So these three are going to be reciprocals to its inverse reciprocal functions might be the correct term there, or reciprocal identity functions. I have to find that word for you. But basically, sine pairs with cosecant. So then the cosecant of theta is just going to be the reciprocal of sine, which will be 13/5. And then the cosine will be paired with the secant, which is the reciprocal, which is going to be 13/12. And then the tangent pairs with the cotangent, which will be 12/5. So those are the first 6 ratios. We can then take, remember these are all from the vantage point of theta. Well, I could also find these 6 ratios from the vantage point of alpha. And we should have some of the same answers, kind of, some of the same numbers, but they go for the different ratios. For instance, if I take the sine of alpha, that's going to be opposite over hypotenuse, which is 12 over 13. Well, that should be the same as the cosine of theta. And then the cosine of alpha should be the same as the sine of theta, which is 5 over 13. And then the tangent of alpha should be the same as the cotangent of theta. So that's going to be opposite over adjacent, which is 12/5. And that's really all where the work needs to go, because then the next 3 are just going to be the reciprocals of these 3. So instead of the sine of alpha, we're going to have the cosecant of alpha being 13 over 12. Again, going to be the same thing as the secant of theta. And the secant of alpha being the reciprocal of this, which is 13/5. And then the cotangent of alpha being the reciprocal here, which is going to be 5/12. So the last thing we discussed was this idea of cofunctions. So cofunctions, meaning its opposites are going to be the same. So the sine of theta is the same as the cosine of alpha, which means sine and cosine are going to be cofunctions. Similarly, secant and cosecant are cofunctions as well. And then tangent and cotangent are going to be cofunctions. So these are going to be the same values, but with the opposite reference angle. So that wraps up kind of a very brief summary of our trig ratios before we get more into what we learned about the unit circle and how all of those angles play into these as well.